Okay, so I backed this up and I'm just reviewing what we've talked about as I started the recording. Should have started it earlier. I apologize for not doing that. We read through this background information about the Cassini mission to Saturn, which took 6 years to get there. And at the very end of its mission, they actually dropped the probe into Saturn's atmosphere, where the rocket was destroyed. But it had many years to make measurements at Saturn, including spectrographs. And so what we're going to do is look at two spectrographs. One is a measurement of the light coming from Titan's atmosphere, which of course tells us what elements it's made of. And the second spectrograph is the light coming from Saturn's rings. So here's the spectrograph from Titan, and I've written all over it, but I want to show three things in particular. One, there's a big spike at about 1200. And when we compare that to the spectrograph from hydrogen, we see that hydrogen also has a peak at that same place. So that makes us think this big peak is hydrogen, represented by the letter H. However, krypton also has a peak at 1200. So how can we tell the difference? Because krypton actually has a double peak. There's a small peak before the 1200 mark. And we do not see that in Titan. We only see the single peak. And that makes us think that that most likely is a peak from hydrogen, not from krypton. The next part of the Titan spectrograph is down here in these wavelengths between 1300 and 1700. And it's hard to tell because they're just a bunch of little wiggly lines close to the axis. So they zoomed in on it and expanded it, and we see all these different peaks. So now we're going to compare that little section to the four elements that we have to work with. Doesn't look like it matches either hydrogen or krypton. They don't have anything going on between 1300 and 1700. So then we come down to helium. Once again, helium is a double peak, but it doesn't have these multiple peaks like we see over here. But nitrogen does. They're the right number. It's between 1300 and 1700. It's got all kinds of peaks going on, and that makes us think that the atmosphere of Titan also has nitrogen. When we zoom in and look at that part of the spectrograph, we can see all of this must be for nitrogen. Then there's one more part of the spectrograph where I've drawn this arrow, where we have a bunch of activity between 1700 and 2000, maybe 1700 and 1900, which doesn't seem to match any of the spectra that we've been given to work with. So that could be another element that we just haven't learned about yet, or it could be noise that was accidentally included in the spacecraft's signal. Kind of like when you're listening to the radio and there's static, that is what we would call noise. Then we went down to this page, and we should be pretty much done with answering these three questions. How are we doing out there? What do you got? You got three done? Yeah? Doing okay at home, I hope? So let's move on to the next part. And highlight along with me. Now, the next couple questions, you're going to use this information that we're about to read together to help you answer the next set of questions. Okay? So what we're looking for is explanations for why different elements would be present. Where did they come from? When were they formed? Stuff like that. So keep that in mind. Here we go. As you saw in the spectrograph, Titan has a thick atmosphere consisting mostly of nitrogen, similar to the Earth's. The gravitational properties of a large moon like Titan are very different from those of a debris field like the rings. Titan's gravity captures atoms like nitrogen that would otherwise escape to space. Unlike Titan's atmosphere, Earth's atmosphere contains oxygen, mostly a result of photosynthesis. I'm going to stop here for a minute. Let's back up to this business about gravity. So Titan and Earth are pretty large objects, so they have a lot of gravity, huh? On the other hand, the rings are many small particles. The biggest is only the size of a mountain. So how much gravity do they have? Not very much, huh? So would they be able to trap and hold a gas like nitrogen if they didn't have very much gravity? Seems unlikely, huh? But an object with more gravity could trap and hold that gas. Okay, so we're thinking about explanations for the presence or absence of different molecules. So nitrogen is going to involve gravity. Let's go back here. Unlike Titan's atmosphere, Earth's atmosphere also contains oxygen, mostly a result of photosynthesis. Before there were plants, we did not have oxygen in our atmosphere. We might speculate that Titan has no plant life, at least as we know it, because Titan's atmosphere lacks oxygen. So if you think back to your biology class, photosynthesis occurs in plants where they take in carbon dioxide and water, and using light, they build sugar, and they have a waste product that they release back into the air called oxygen. Now, from our viewpoint, it's not a waste product, is it? But that's where the oxygen in our atmosphere came from. We see no oxygen in the spectrograph from Titan. Therefore, do you think it has plants? Seems unlikely, huh? Meanwhile, hydrogen. It is the simplest of all elements. It is a single proton orbited by one electron. It makes up about 73% of the mass of the universe today. Most of the universe is made of hydrogen gas. We think this simple element was the primary type of matter formed during the Big Bang about 13.5 billion years ago. Since then, fusion in stars has converted much of this hydrogen into helium. So helium is the second most abundant element, making up about 25% of the mass of the universe today. As stars continue to fuse hydrogen into helium, we can predict that the amount of hydrogen will decrease while helium will increase in the future universe. So here's what's going on. The Big Bang made all these hydrogen atoms. In the sun, there's incredible pressures that squeezes them together. And when you take a couple of hydrogen atoms and squeeze them together, they stick together and they turn into helium. But part of that process releases energy in the form of light. That's why the sun is making its own light, is from this process of fusion. To fuse something means to glue it together. So we take 4 hydrogens, we squeeze them together, it gives off light, the resulting new atom is helium. So I want you to use the information we just read about to answer the next 3 questions, I think. Yeah, and notice they say, explain why. That means it's a longer answer, huh? Before, when it just said list the elements, that's very short. Now you have to explain why. You're going to have to write a couple sentences. So take a couple of minutes to do that. I'll give you a hint on the first one. What's the most abundant element in the universe? Just read it to you. What is it? Hydrogen is the most abundant. That means it's pretty much everywhere we look in space, huh? So even if you're looking at the rings, you could be looking at light from behind them too, huh? And measuring the spectra of whatever elements are out there in space. Yes. Yeah. Yeah, it should be on the counter here. Will you check and see if it's hanging on the hook? Yeah, I will. All right, how's it going, guys? You finished those three? Did you give me a good explanation? One of them, you need to talk about gravity. One of them, you need to talk about the Big Bang and how it's just everywhere. And the other one, you need to talk about plants and photosynthesis. Just as a little hint. All right, that finishes our analysis of the spectra from Saturn. We're going to move on to a new assignment, basically. You could think of these as separate assignments all combined together in this big project, huh? And this one's called Goldilocks and the Free Planets. So what's the story of Goldilocks say, anyway? What does she say over and over again? This one's too hot. This one, too cold. But this one's just right. Or this one's too small. This one's too big. But this one is just right. And that's what we're going to do here. We're going to look at the Goldilocks effect. We're going to compare Venus and Mars to the one that's just right, the Earth. Huh. Highlight. What do you know? We never do that in here, huh? Here we go. You've probably heard about the greenhouse effect and global warming. But did you know that if the Earth had no greenhouse gases, our planet would be colder? In fact, it would be too cold. Greenhouse gases act as a blanket that keeps us warm because they trap some warm radiation from the sun. Too much of a good thing can be really bad, though. If we have too many greenhouse gases in our atmosphere, we could warm the planet up too much. By the way, I'm seeing that I have a spelling error that I did over and over again. Gases should not be a double S. It should just be Gases. So I apologize for the spelling mistake. Some nearby planets, Venus and Mars, also have greenhouse gases. You've heard the story of the three bears. This is the story of the three planets. Venus is much too hot. Mars is much too cold. And Earth is just right to support life. There is more to the story than you might initially think, though. And your job will be to figure out what other things or variables, besides greenhouse gases, what other things affect the temperatures of the three planets. Engineers built spectrographs for spacecraft that traveled to the planets Venus and Mars. One of the goals was to find out what gases make up their atmospheres. These spacecraft sent data back to Earth. The spectrographs found the spectra of Venus and Mars by looking at light from the two atmospheres that originally came from the sun. So wait a minute, let's look at this spectrograph here. Would you say this is an emission spectrum or an absorption spectrum? Did this yesterday. We had some graphs like this one that were up high and every now and then they dropped, right? And we had another one that was down low and every now and then it spiked. Which is this one that has the drop? Is this an emission or an absorption? Good job. This would be an absorption spectrum. When it holds on to that light, huh? Yeah, it's like icicles, uh-huh. When you look at a spectrum taken from a spectrometer, you can figure out what is inside of that atmosphere because the dips and peaks in the graph match up to the known dips and peaks of gases that scientists and engineers have measured in laboratories. You will be using actual data from spacecraft and data taken in the laboratory to figure out what is inside the atmospheres of Venus, Mars, and Earth. Part one. First, let's compare the spectra of Venus on the top and Earth on the bottom. The spectrum of Venus was taken from the Venera 15 spacecraft with an instrument called the infrared Fourier spectrometer in the 1980s. The spectrum of Earth was taken by the Nimbus 4 spacecraft, which orbited Earth in the 1970s. Compare the dips in the planet's spectra with the spectra of known elements on the following page. Be sure to look at the scale very carefully, the numbers across the bottom and the numbers on the side. Notice that the x-axis is backwards from what you might expect. Our 0 would be over here on the right, huh? So be careful. Try to find which elements show dips in the same places as the planetary spectra. So if you go to page 13, there is nothing to read there. It is just, I think, 6 different elements or molecules. Yeah, some of these are elements, some of them are compounds. 6 different molecules, all of them absorption spectra, right? So pay attention to where the dip happens and how many dips there are. Compare this to Venus, compare it to compare it to Earth, and then go on to page 14 to start answering questions. I want you right now to do the first 4 questions by yourself. And then if you look at number 5, it says, let's do some math. So I'll be back to help you with that part, okay? All right, go ahead and answer questions 1 through 4 on page 14. You'll need to go back and forth between page 12 and 13 to compare the spectrum from Venus to the spectrum of the different molecules. And the same thing for comparing Earth to those molecules. Let me know if you have questions. right, show me how many fingers. Did you answer all four? Done three of them? Two of them? Only one? Need a little more time? Okay, I'll give you another minute to work on those four. Thanks, Hans. Okay, let's move on and look at this mathematical analysis. So, just how much CO2 do the two planets have in comparison to one another? It's kind of hard to compare because our atmospheres are different thicknesses. Our atmosphere is not as thick as Venus, but it's thicker than Mars. So we have to adjust our comparison to account for that. So, part A, Venus has 90 times more atmosphere than Earth does. It's about the same size as Earth, but its atmosphere is much thicker. It's much denser. It'd be like walking around in fog, except the fog would be so thick that you could feel it on your shoulders, pushing down on you. Yes, and not only that, the fog is made of acid rain. And it's like 900 degrees. So it wouldn't be very fun. At any rate, to show that Venus is 90 times more atmosphere than Earth does, we're going to use an algebraic expression where the way we read this is A sub V. What do you think that stands for? What's the A? What are you talking about? A is going to be atmosphere. A sub V would be the atmosphere of Venus. So A sub V equals 90 times, right? 90 A sub E. So please write down, what does A sub V stand for? What does A sub E stand for? Make sure you ask if you don't get what I'm talking about here. So A is the atmosphere. If it has a V next to it, which atmosphere? The atmosphere on Venus. If it has an E next to it, it is, what if it were, well, what would it be for the atmosphere of Mars? What letter would we use? We'd use A sub M, huh? Exactly. Part B. About 0.04% of the total mass of Earth's atmosphere is carbon dioxide. Algebraically, E sub CO2 equals 0.0004 A sub E. Now, what was A sub E again? The atmosphere of Earth. So 0.0004 of Earth's atmosphere is carbon dioxide. What do you think E sub CO2 stands for? E is going to be what? Earth. Sub CO2 tells us that we're talking about the amount of carbon dioxide in Earth's atmosphere. Make sense? E sub CO2, the amount of CO2 in Earth's atmosphere. About 97% of the total mass of Venus's atmosphere is carbon dioxide. Look at that, 97% CO2. For us, it's way less than 1%, isn't it? For Venus, 97%. So V sub CO2, 0.97, A sub V. Go ahead, answer that question. What does VCO2 stand for? V sub CO2. You answered B, you should be able to answer C, but you just got to change it a little bit, huh? Are we okay with that? We're talking about, you should start both, your answers to B and C should both start with the amount of, yes, the amount of, what molecule are we looking at here? And then tell me where we're talking about. All right? Part D. Now, we can combine these algebraic expressions to find out how much CO2 is in the Venusian atmosphere compared to Earth. Please complete the calculation by using this equation. A sub V. You need to plug in the numbers now, don't you? And you need to get out your calculator. A sub V is given to you up there in letter A, huh? A sub, oops. Again. A sub V times VCO2 divided by E sub CO2. Right? Do you have all those numbers to plug into your calculator? Multiply first across the top and then divide into the bottom, huh? So go ahead, get out your calculator. Multiply the correct numbers. You should get a pretty big answer. Do you agree? So when you multiply this out and then divide, your answer should be pretty big. Like if you put a dollar sign in front of it, that would be a pretty good income for a year. More than a teacher makes, I'll tell you that. Now, this is actually the same answer as number 6. What we've just calculated, to put that in perspective, is why number 6 is there, and you repeat your answer. It's telling us that Venus has that much more CO2 than Earth does. For every 1 molecule of CO2 on Earth, Venus has that many more molecules. So if CO2 traps heat, what's going to happen on Venus with all that CO2? Hot enough to melt lead. Not the lead of a pencil, but I'm talking about the metal. Lead, the metal. It's a very heavy material. On Venus, it's hot enough to melt it just by being out there. So let's see. What reasons can you think of that might explain Venus's hot temperature? For number 7. Hey, do you guys know the order of the planets from the sun? Uh-huh. Uh-huh. The memory tool that I use, it includes Pluto at the end, because Pluto is still there. Whether we define it as a planet or not, it is still present, right? It's not like it disappeared. It's just that we've changed our definition of a planet, so Pluto doesn't really count as a planet anymore. But here's the memory tool that I use. You take the first letter of each of these, and you'll have the first letter of the planets in order from the sun. It goes like this. My very excellent mother just sent us 9 pizzas. My very excellent mother just sent us 9 pizzas. So, what order is Earth then? What? Going from the sun outwards, Earth is number 3. Where's Venus? So is Venus closer or further from the sun than we are? Okay. Would you expect it to be hotter or colder if it's closer to the sun? Something to think about. What about the first M? That's the second M. I know it's confusing because there's 2 M's, huh? Yeah. This one's Mercury. And this one is Mars. J? S? Uranus. And it's not just that we're afraid to say anus, okay? I'll say it. I'm a biology teacher. It's part of the digestive system, right? It's because in Greek it actually is pronounced Uranus. So, does it bug you when people say Nevada? Okay. It bugs me when people say Uranus for the same reason. It's just not the way you're supposed to pronounce it. The same thing is true for Halley's Comet. The guy's name was Halley. His name was not Haley. But what happened, you guys know what I'm talking about? Have you heard of Halley's Comet? Most people mispronounce it as Halley's Comet. What happened in our country, in the 50s, there was a band, and the leader of the band was Bill Haley, and he named his band the Comets. Bill Haley and the Comets. Pretty cute name. But actually, the guy that the comet is named after is an English scientist, and his name was Edmund Halley. So in our country, since the 50s, we've been mispronouncing it. It's Halley's Comet. It's Uranus. It's Neanderthal. In Germany, there is no TH sound. It's not Neanderthal. And they've discovered the first Neanderthal fossils in a valley called the Neander Valley. And in German, a valley is known as a Tal. Tal. I'm not sure where the H came from, but it should be Neanderthal. So just like we have Nevada, we have Uranus, Neanderthal, Halley, or we could go Nevada, Haley, Neanderthal, and Uranus, and mispronounce them all, huh? All right, so get number 7 answered. Again, letter D and number 6 should just both be the same answer, shouldn't they? I'll give you a hint on number 7. I'm looking for 2 reasons that Venus is so hot. I'll be looking for 2 different reasons. One of them has to do with my very excellent mother just sent us 9 pizzas. And the other has to do with what we were doing the math about. Okay, 2 reasons that Venus is so hot. Hey, what would you expect? What would you predict? Is Mercury or Venus hotter? Mercury's closer to the sun, huh? But guess what? Mercury has no atmosphere. It's a small planet, and being very close to the sun, that means there's a lot of energy coming onto the atmosphere, and basically it's lost all its gases. It's airless. So is there any CO2 on Mercury? No. Is there anything trapping the heat there? No. Venus is actually hotter than Mercury. Is that what you would expect based on their position? But what does Venus have that Mercury doesn't have? Oh. Right? So there's 2 reasons that Venus is so hot. Actually, on Mercury, if you're on the nighttime side of the planet, you freeze. When you're facing the sun, you cook. It's like 700 degrees. Yeah, you're cooking on this side and you're freezing on that side. It's like one of those burritos you put in the microwave and only half of it got melted, right? Okay, this is what we're going to do. We have another 20 minutes of class. We don't have time to do part 2 on page 15. Okay, so we're going to skip part 2 and we're going to jump down to page 17, which is a different, shorter activity about the solar spectrum. Okay, so we're going to jump ahead to page 17 and get that finished. Are we ready? Am I going too fast? Okay, so the solar spectrum. The brightest star in our sky is the sun. Absorption lines, oh, and of course, what are you doing while I'm reading? Absorption lines in the solar spectrum were first noticed by an English astronomer in 1802. But it was a German physicist, Joseph von Fraunhofer, who first measured and cataloged over 600 of these absorption lines about 10 years later. These lines are now known collectively as the Fraunhofer lines. And you can see some of them are labeled in this absorption spectrum. How can I tell that's an absorption spectrum? It's got the dark lines that are missing from the spectrum, huh? Because those colors have been absorbed. In the 1800s, scientists did not know that these lines were chemical in origin. Thus, the letters used by Fraunhofer to identify the lines have no relation to chemical symbols, nor to the symbols used to designate the spectral types of stars. Today's astronomers use some of the designations simply for convenience and ease in identifying lines. So, for example, here's the H line, right? If we're looking at the periodic table, H represents hydrogen. But this H line has nothing to do with hydrogen. It was labeled H before they realized that it's the elements that are causing these things. Does that make sense? You can also see that there's major lines and there's also minor ones. See the lowercase letters in there? Most of the major ones are really thick. Yeah? Does that make sense? Notice that there are both major and minor absorption lines shown above. Each element forms multiple spectral lines when it's heated. Remember, they make multiple lines. Like, was it yesterday that I gave you an unknown gas and like 5 or 6 known gases, and you had to figure out which one it matched? Every one of those gases had 5, 10, 20 lines, didn't it? So imagine not only 5 or 10 or 20 lines, but more than one gas at the same time overlapping. That's what we're seeing here in the sun. Multiple spectral lines from multiple gases. Each element forms multiple spectral lines when it's heated, and the sun is composed of several different elements. Identifying the elements found inside the sun by analyzing these spectral lines is kind of like looking at several overlapping fingerprints at once. So we will use a simplified version of the solar spectrum here. Use the table to label each of the spectral lines with the element symbol. So, if we look at this spectrum, we can see it's going from short wavelength to long wavelength, from violet, indigo, blue, green, yellow, orange, red. But it also reminds us that beyond that, we have the infrared. Remember, infrared is not the same as red, huh? You can see red, but you can't see infrared. However, because it's the same as heat, we can feel it, huh? Similarly, on this side, ultraviolet means it's beyond the violet. It's not the same as violet. You can see violet. Can't see UV light, but you can get sunburn from it, huh? So what we're going to do is we're going to take Fraunhofer's spectrum and we're going to simplify it down here. See how that's a little simpler? It doesn't have so many lines to worry about, right? Your goal is to name what element produced each of these lines by using this table over here. So here's what we're going to do. We're going to look at the table, and for example, this one is at 393 nanometers. That's not even on the chart, is it? So does this line get included? No, not all of these are present. Only some of them are present. When I look at this line, and I don't know why this is a weird double arrow here, but anyway, what number is that? Oh, it's a little less than 440, huh? So I want to look for a wavelength that's a little less. Oh, is that a little less than 440? The 434 line. That looks pretty close to 434. I think that must be it. So I'm going to label this as H for hydrogen. Just put the symbol on there. You don't have to spell out the whole thing. So you just label each of these arrows, label each of these lines by using this chart. And keep in mind that not every element on the chart is in the spectrograph, right? Some of the elements are on there more than once because they produce multiple spectral lines, huh? Go ahead and label all of those and then answer the 3 questions. Oh, and on this question, I want you to give the full names. You get to number 1. Use the abbreviations on with the arrows But give me the full names of the elements down here on question one. Okay, just want to point out, if you think you're caught up in here, that means you finished pages 1 through 14 and page 17 in the project, and you've also done the Aurora's assignment, right? That means you're caught up in this unit. Did I ever, you guys had a chance to look at your tests?
Yeah, you did it.
You saw the test? Okay. So I want to remind you that you have the opportunity to raise the grade on your test. Just come talk to me about how to do that, and we'll set a time when you can make that happen, okay? Let's see, today's a B2, so I won't see you till like Wednesday next week. Is that right? Okay. Well, have a good weekend, you guys. Good luck in your games this week and all of that. I'm going to sign out, so I'll talk to you later.
Thanks, Fairly.
See ya. Remember, I'm not going to give you guys calls anymore. You got to tune in on your own.